Hi, I'm Rich with Inside HPC. We're here at PASC 17 in Lugano, and I'm here with Yasuhiro and Laurent. And I understand you guys are both experts in high-energy physics. What brings you to Lugano?
Well, what brings us to Lugano is the unique opportunity to share our experience with fellow researchers. So we know each other, by the way. Yasuhiro, my colleague here, spent some months at EPFL some years ago, and we exchanged ideas at that time, and this is again an opportunity to meet also scientists from other fields in computation.
Yeah. So why is that important for you to come all the way from Japan to a conference like this? What do you gain from networking with people that have the same interest in physics?
This conference has a wide spectrum of participants, ranging from different application domains and computer scientists.
Yeah.
And we have very unique opportunity to exchange our knowledge and to advance co-design of the next generation simulations. So I think this kind of interdisciplinary meeting is very beneficial for all of us.
So why do we need HPC to better understand high-energy physics?
Yeah, actually we are working on fusion science, plasma physics.
Yeah. So that's hard to measure in the real world, isn't it? I mean, you can't like stick cameras into the reactor and things like that, right? So you have to simulate it, right?
Yeah. So we are dealing with a very high temperature plasma, which it is very difficult to measure such high temperature plasma from outside. So simulation is very powerful tool to understand turbulent transport in fusion reactor. And now we are working on current experimental devices, which is small or medium size. And our next generation experiment, ITER, will be huge machine. And we need very big exascale machine to compute ITER plasmas.
So how daunting a challenge is designing a fusion reactor in terms of simulation?
Well, that's a multi-billion-dollar question. In terms of, say, the experiment is multi-billion dollars, so it's a multi-million-dollar question for simulation, which is much less. But still, the daunting question is that you have to imagine a kind of a medium where the temperature is 100 million degrees in the center, and the edge is, you have magnets which are at minus 270 degrees. So you have strong gradients of temperature, in other words, and therefore plasma, which is the hot gas that we are simulating, has natural tendency to spontaneously evolve into instability, like we have thunderstorms when the air becomes unstable and develops convective cells, as we call, and then it rains and wind blows and all sorts of unhappy things can happen. In the plasmas, it does not rain because the temperature is much too high for liquid, but we want to simulate this because this turbulence is like mixing up the things. Imagine a soup where you want to heat the center of your dish at very high temperature but keep the edge very cold. If you start to stir your soup, the temperature will be equalized and the hot parts will hit the cold walls.
I see.
So you want to be able to understand that, understand the existing experiments, as Yasuhiro said, but also to predict the future experiments. So that's, I mean, the equations that you are solving are typically several billions of equations that we have to solve simultaneously for several hundreds of thousands of time steps. So this gives you just an idea that high-performance computing is absolutely essential.
Well, one question I always had about the way the sun works, right? It puts out a lot of radiation, and today's nuclear reactors, the problem is that that they put out. Will fusion have the same problem, or will it not be? Why? Because there's so much energy. I don't understand.
There are two differences
Yes.
with existing nuclear plants. The first is that the basic physical reaction is just the opposite. In our fusion reactors, we are going to fuse hydrogen into helium. So we are going to produce helium. Helium is not radioactive, is not a greenhouse gas, and the way we are going to do it is not in a pressure vessel, it's in a vacuum vessel. So the plasma we are talking about is 100 million degrees in temperature, but it has 1 million less density as the atmosphere that you are breathing at the moment. So in the end, the pressure in the plasma of ITER, for example, the fusion reactors is only 2, 3, 4, 5 atmospheres. So the same pressure as the pressure of your tires on your bike.
Okay.
So, and it's not a chain reaction, so no divergence, explosion reaction. It's a burning.
Oh, it's burning, it's not a chain reaction.
No, and the amount of fuel that you put in the plasma at any given time is only 1 gram.
Okay.
There's only 1 gram in the core of a fusion reactor.
That's all?
That's all, and you have to fuel it constantly,
Yeah,
like a lighter. You have to fuel it, and it burns. But the amount of gas you have in a flame is tiny. It's the same. So no, fission reactors like the one which there was this mishap in Fukushima or the one in Chernobyl. The problem is that there is 100 tons of fuel in the
a lot of radioactive material.
Which is radioactive and so on,
Okay.
which is fissile, which is, everything.
And you're talking about a gram of hydrogen?
And it's a 1 gram, 1 gram at a time, that you're putting in.
Okay.
So no greenhouse effect. The fuel is abundant all over the place. No long-term waste disposal, no risk of explosion. No risk of
Catastrophic.
of nuclear explosion
right,
in this
right.
sense.
I got it.
No.
Okay.
So that's a very big challenge.